Let us start. We are going through our third module over the torsion. I have discussed what is torsion, what is exactly meaning by this phenomenon torsion. We are dealing with prismatic bars of various size, of various lengths, mostly of round cross section. This bar is supposed to be loaded by different external loads, which may be tensile, maybe compressive, maybe bending, maybe torsional, or maybe twist, maybe torque. So one type of load which may exert over any prismatic bar is a torsional load or a load of twist or load of torque. What is this? You are twisting a bar by means of two parallel forces of same magnitude, but line of action is different. They are acting on the two mutually perpendicular surface of the cross section of a bar, say round cross section, and they are, as a result, they are starting twisting of the over the bar. We are supposed to go how much twist, what can be the maximum torsion or torsion moment this part can exert, what is the shear force which can be exerted due to the effect of torsion and over different section, what is the value of the shear forces when from the center of the cross section to the outside radius of the cross section, what is the variation and where is the maximum. And we have reduced a few equations like torsional equation to reduce what can be the, this is the torsional equation here. We have reduced the torsional equation.
सर एक क्वेश्चन है, टॉर्शन और टॉर्क दोनों सेम होता है क्या?
Yes. Look, what is torsion, what is torque, what is twist, what is couple? They are all equal to each other. They are same. But what is that? There are two types of forces, rectilinear forces and torsional forces. What is rectilinear? This is acting on a straight line. The force may be tensile, may be compressive, may be bending, but it is acting on a straight line. And it is single. It is not a number of forces acting at the same time. How it is acting? This rectilinear force is acting along the longitudinal axis of a, say, prismatic bar of, say, round cross section of any length. This rectilinear force can be tensile, it can pull the rod, it can be compressive, means it is compressing the rod from the both ends, and it can be bent. How it is bending load is acting? Bending load is again a single point load which is acting normal to the longitudinal axis. So you see there are two lines of action along the longitudinal axis and normal to the longitudinal axis. But force is same, a single force, a single point load which is acting normal or along the axis. This single point load can be different. It can be distributed load. It can be a twist there even. That's a different story. I will tell you if I have time permits. But there is another type of force. There is another type of force which is called skew. S-K-E-W. Skew means they are acting, they are not parallel to each other, but they are at an angle with each other, but they are not intersecting each other. This is a skew force, but it is not beyond our point of discussion. There are another force that is couple or torque, which means a force of, say, F of any magnitude is acting, and another force of same magnitude is acting parallel to the formal force of the same magnitude. Says one is F, another is F, but their line of action is exactly opposite. One is acting towards, maybe towards you, and another is away, acting away from you. Okay, but they are of same magnitude, but they're acting parallel. They are acting parallel. If they, in such a way, if they exerted over any prismatic bar, they will twist the bar by the action of force, maybe in clockwise direction, maybe in anti-clockwise direction as per their line of action. This twist, this couple, this is called twist. This is called a couple. This is called torque. This is called torsional moment. Most widely used the torsional moment. These are same. This is creating a twist over the bar, which is defined or known as most probably known as torsional moment, which is acting over the bar. So how, due to the twist over the bar, which is creating by the action of these two parallel same magnitude forces, but line of action is exactly opposite and they are parallel to each other. This is, we are supposed to investigate how does this affect our bar from our subject point of view, which means here we are supposed to investigate what is the shear stresses resisting forces acting over the created in the bar due to this torque. We found that a shear forces acting over the each cross-sectional section of the bar. This shear forces is maybe zero at the central at the longitudinal section at the center of the bar, and maybe maximum at the outer radius of the bar. And how much shear stress a bar can exist, how before it is breaking, we are supposed to calculate, we are supposed to know, we are supposed to find out. And in order to know so, we have established a relation here, that is the relation over between angle of torsional moment or torque, that is T. J is the polar moment of inertia, means that it is the second moment of inertia of the cross section of the bar. Tau is the shear stress induced in various position bar. What is the various position? This position is being defined by the radius, is the distance from the center of the cross section to the outside radiation, and tau is the shear stress induced at a distance r from the center. G is the polar modulus of rigidity, and theta is the angle of twist in radian. Find that it is induced in radian, not in degree. And L is the total length of the bar, starting from the point of fixing, end of fixing end, or to the line of action of the torque. So this is defined as torsional equation. And now, based on this torsional equation, we have investigated the torque and other aspect of a solid bar as well as a hollow bar. We are in this position, we are always discussing the round cross-sectional bar, which can be solid or which can be hollow. But it is possible that it can be other cross-section also. Here, as we say, for the solid cross-section, the polar moment of inertia, its circular shaft is going to be pi by 32 due to the power 4. We have discussed in your inertia moment of inertia chapter. The maximum shear stress will deduce from the torsional equation will get tau is equal to 16t divided by pi d to the power 3 at the outermost surface of the bar. For the hollow shaft, this polar moment of inertia is pi capital D to the power 4 minus small d to the power 4 divided by 32, is where capital D is the outer diameter of the bar, small d is the inner diameter of the bar. And maximum shear stress induced is given by 16 capital D into D divided by pi capital D to the power 4 minus small d to the power 4, where torque T is the torsional moment or torque or twist acting over the bar, and T is the outer diameter of the bar, and small d is the inner diameter of the bar. There are other few important definitions we have deduced. One is called torsional. One is called, first of all, the most important is the maximum value of shear stress. The maximum torque which can be carried by a given section of the bar for a given maximum value of shear stress is defined as torsional moment of resistance or resisting torque. So here comes, first of all, the situation, what can be the maximum torque you can apply over a bar? What is the maximum, that is the maximum limit of the torque which a bar can carry, which depends on for a given maximum value of shear stress. Shear stress of a particular material is fixed it varies from material to material. For steel, for aluminum, for brass, this is all different, but there is more or less unique shear stress. But actually it is not like this, but we think that these have a more or less average or unique shear stress for each of them, but they are different from material to material. Now, as per the maximum shear stress a bar can exert, what can be the maximum torsional moment it can carry, which is defined as the torsional moment of resistance or resisting torque of the bar. So It is the sum of the moments of all tangential shear stress acting in cross section. Shear stress can be multiple, can be a number of different couples can act over it, but the maximum limit of torsion which it can carry is the torsional moment. Next, another equation, J divided by R, means the polar moment of inertia divided by the radius R is defined known as polar section moment. This is another definition defined as torsional or polar sectional moment. Then torque per radian twist, also known as torsional stiffness, means T, the torsion per radius divided by the T divided by theta is J into G divided by L. This is given as torsional stiffness or K. The parameter G into J, G stands for modulus of rigidity, J stands for polar moment of inertia defined as torsional rigidity of the shaft, similar to the flexural rigidity of a beam, which we'll go through when we'll go through the bending stress. Thus, from G into J, or torsional rigidity is given as torque divided by theta divided by L. The torsional rigidity also torque per unit angular twist. Per unit means per unit length. Angular twist per unit length. So torque per unit angular twist is given by the torsional rigidity or G into J. We know the power transmission, a shaft is meant for transmitting power from one position to other, from motor to the say lathe, from engine to say the different rear wheel of the car, say from turbine to the alternator, turbine to the alternator of a turbine to the alternator of electric generator. So this how much the power can be transmitted for a given torque, or which is limited by the maximum torsional moment or maximum twist which a bar can exert, is given by this relation P is equal to T into omega, where T multiplied omega is 2 into pi into n divided by 60, where n stands for RPM of the or revolution of the shaft in per PM. So its equation becomes 2 pi n T divided by 60. These are the two important relations which we deal and investigate through our analytical problems here. Let us go through again a few problems to finish this portion of the chapter. That is 7. Now, here this problem, a 2 meter long and 40 millimeter diameter aluminum shaft is supposed to be replaced by a hollow shaft of same length and same outside diameter with the same angle of twist. 1 second. Same angle of twist over the total length. Determine the inside diameter of the hollow shaft. Take the modulus rigidity of the steel, thrice that of the aluminium. So what is given? Length of the shafts is given. That is 2 meter. Diameter of the shaft. This is the outer diameter of the shaft. It is to be shaft is this solid shaft. Aluminium shaft is solid. Aluminum shaft is to be replaced by, but it is replaced by a hollow shaft of the same length of same outside diameter. So steel shaft has the length equal to 2 meter and the outside diameter equal to 40 millimeter. But it was made of steel, not made of aluminum. And with the same angular twist over the total length. So it can make the same angular twist theta over the given length 40. So let us decide, we are supposed to determine the inside diameter of the hollow steel shaft. What is given is there's a relation, the modulus rigidity of the steel is 3 times that of the aluminium. So what is given here? Length of the steel and aluminum steel shaft is given. Outside diameter of the steel shaft is also given. The modulus relation between the modulus of rigidity of steel and aluminum shaft is given. And another thing is given. Thus, both steel and aluminum can sustain the same angular twist over the entire length. So here we have to calculate that inside diameter of the hollow steel shaft, which is not unknown to us, but outside side of the is known to us. So what is given? Given here 40 millimeter aluminum shaft, 2 meter length. And we are supposed to determine the inner diameter, and torque is also given. GS is equal to 3 times G. Now, D becomes the inside diameter of the hollow aluminum shaft. Now, in the relation of torsional indication, this portion T divided by J is equal to G into theta by A, where T stands for turning moment and J stands for axial polar moment of inertia. G stands for modulus of rigidity, theta angle of twist, divided by L is the length of the bar. And here torque is same, L is same, length is L, length is same, theta is same for both aluminum and hollow bar. So what is becomes G is S equal to, if we equate like this equation can be written as T into L here by theta, which is equal to G into J. Now, what is given is this for the T torque and length and angular twist are same for both the shafts. So G into J for aluminum means the modulus rigidity for the aluminum shaft is multiplied by the polar moment division of the aluminum shaft is equal to the same for the steel shaft, which is given as GS, JS, which is for steel, and G0, J0, which is for aluminum, GA, JA, aluminum. So, polar moment division of the steel can be written as 3 G into A by GS into JA. I know now G into J is a ratio we know, which is 1/3. GA by GA, GS is equal to 3 into GA. So GA by GS is equal to 1/3. So this we know the relation, and thus if we put the value of polar moment of inertia here, it is equal to pi by 32 for d to the power 4 minus d small to the power d to the power 4 capital D, because the steel shaft is hollow and capital D is the outer diameter of the steel shaft and small d is the inner diameter of the steel shaft. And this is equal to 1/3, means 1/3 is the relation between GA and GS is equal to pi by 32 into d to the power 3, where D is the diameter of the aluminum shaft, because we know that diameter of the outer diameter of the aluminum shaft is equal to that of the steel shaft. So we have got this relation. This is, we are cancelling each other here, and so what we have, and D will come here to make it d to the power 4. So what we have, d to the power 4 into d square d to the power 4 is equal to 1/3 d to the power 4, or this will become 2/3 2 d to the power 4 into 2/3, or 2/3 into 3 to small d to the power 4, or d to small d by capital D is 2 by 3 to the power 1/4, or which is equal to 0.9036. And thus, inner diameter of the steel shaft is given as 0.903 multiplied by the outer diameter, which is known as equal to 40, is 36.14 millimeter. Now, let us go for the next problem. This is problem number 8. The cross-sectional area of what is given. Cross-sectional area of a solid shaft, 160 millimeter diameter, is the same as of a solid hollow shaft of the same material of 120 millimeter inner diameter. So, what is given? So we have got a solid shaft whose diameter is known. So their cross-sectional area is known. Diameter is given as 160 millimeter, and we have a hollow shaft made of the same material whose inner diameter is known, but they are of same cross section. So if the cross section area is same, then we can, from here we can calculate the outside diameter of the hollow shaft also. So what we have to find out, the ratio of power transmitted for the same angular velocity. Next, this is the angle of twist for the equal length when stretched with the same intensity. So first of all, what can be the power transmitted with both of them? when they are running with the same angular velocity. So ratio difference in power consumption, that's we are supposed to find out. Next is, what is the angular twist? What is the ratio of the angular twist of these two shafts? They are when they are of equal length and when they are stressed by the same intensity. When means when they are twisted or torque is same. So what is given here? The solid shaft of 160 millimeter, its diameter is given. Hollow shaft is being known as of the same material and same cross-sectional area, and inner diameter also given. So next, the outer diameter of the hollow shaft, say D. So as the cross-sectional areas are equal, then the cross-section of the hollow shaft is pi by 4, capital D to the power 4 minus inner diameter, which is given as 120. 120 to the power 4 is equal to pi by 4, 160 to the power 2, or D is equal to 200 millimeter. Now, ratio of the power transmitted. As the angular velocity of the two shafts are same, the power transmitted will be in the ratio of the torques. So angular velocity is supposed to be the same. So the power transmitted will be in the ratio of their torques. So first of all, material is same, the maximum stress or maximum available stress is same, or tau is same. So torque of the hollow shaft will be available from this equation, that is T is equal to shear stress multiplied by pi by 16, 200 to the power 4 minus 120 divided by the diameter D. This is the polar moment of inertia. Now, as the torque of the solid shaft is also same, T tau into pi by 16 into T to the power 4. So torque transmitted is same and it is not same, but the shear stress they are exerting is same, and thus the ratio of the power transmitted is given as P by H by P of H divided by PS is equal to T into H is equal to TH by TN. As we know, the power transmitted is given by this formula. P is equal to 2 pi n T divided by 60. So if the torques, the ratio of the both, this is same for steel. This is for hollow shaft. This is for hollow shaft, and this is for solid shaft. This equation will be like this because they are sorry by 60. So this PH by PS will be TH by TS. So TH by TS we know. So this is given here. This torque is same, shear stress is same. So this ratio will become 1.7. So power ratio of the power transmitted to the hollow to the solid shaft is equal to 1.7. So hollow shaft can transmit 1.7 or 70 times more power than the solid shaft. The angle of twist, ratio of the angle of twist is in the relation tau by R is equal to G by theta. Tau by R is equal to G theta by L, as tau by well, it is available from the torsional equation, as tau is the shear stress, L is the length, and G is the polar moment of inertia, modulus of rigidity. As they are of the same material, the tau, maximum shear stress, and the modulus of rigidity is same, and they are told that they are of same length. So for solid steel shaft and hollow aluminum shafts, they are this G, L, and tau is same. So this relation, this tau, this G, and this length is same. Which is not same, that is the radius, and which is not same, that is the angle of twist. So R into S is theta into L, theta into RS into theta S. If we multiply R with theta S and multiply T into L by G, means T into L by G is equal to theta into S, and T into L by G's relation is same for both steel and hollow shaft. So R into S is into theta S is equal to RH into theta S. So theta S, here by theta is RH by RS, which is the 200 by 160. The 200 is the outer diameter of the hollow shaft, 160 is the outer diameter of the steel shaft, which is relation is given as 1.25. So we have got the relation of we have got the relation between theta S and theta H. Next, example 1.9. Just make this 2. Another 300 millimeter diameter steel shaft, what is given in this number? Another 300 millimeter diameter steel shaft is to be replaced by a hollow shaft of the same outer diameter. Hollow shaft, same outer diameter, made of an alloy steel to transmit 32% increased power. This allowable shear stress value of the alloy steel is greater by 30%. The speed is also increased by 10%. So find the maximum inside diameter hollow shaft. Here, the same thing, another type of problem. The relation, the comparative comparison between the steel shaft as well as the hollow shaft. What is given? Not any numerical values, but the relation between various factors of both these shafts. Like diameter of the steel shaft is given, which is solid shaft. Steel shaft is solid, which outside the diameter is given as 300 millimeter, but it is replaced by a hollow shaft whose outside diameter is also given, which is equal to 300 millimeter diameter steel shaft, but inner diameter is not given. We are supposed to calculate the maximum inner diameter, which is possible this type of alloy steel shaft. This alloy steel shaft is supposed to carry 32% more power. So what is the power transmitted by the steel shaft is the steel shaft, the alloy can transmit 32% more power, but the power is not given. Next, the allowable shear stress of the steel shaft is again 30% of more than that of the mild steel shaft. Then speed or speed of rotation is also can be, or RPM is increased, can be increased by 10%. So the power is although not told, it is increased to a certain percentage. Shear stress is not equal of both the shafts, which is increased to a certain percent by 30%, as both the shafts are of same material. One is made of steel, another is made of alloy steel. The speed can be transmitted increased by 10%. So with this thing, how we can calculate this stress? Participant. Now, so only the diameter of the solid shaft is equal to the outside diameter of the hollow shaft, which is given as equal to 30%. Then tau H means shear stress which can be transmitted by a hollow mild steel shaft is 1.3 times, 30% more than that of the solid steel shaft, mild steel shaft. That is tau H is equal to 1.3 tau S. This is hollow shaft. This is hollow alloy steel shaft. This is solid mild steel shaft. So its shear stress, allowable shear stress is equal to it is 1.3 times more than that of the solid mild steel shaft. The power transmitted by the hollow alloy steel shaft is equal to 32% more than that of the power transmitted by the solid steel shaft, mild steel shaft, which is so relation between these two power transmitted is given as pH is equal to 1.32 pH, means power transmitted by the hollow alloy steel shaft is 1.32 times that of the solid steel shaft. And omega H is the speed or angular speed transmitted by the hollow alloy steel shaft, which is equal to 10% more than that of the RPM or the angular speed of the solid steel shaft. So this relation between omega H and omega S is equal to 1.1 into omega S. Let us decide. Now, this D is the diameter of the solid shaft, as is the diameter of the hollow shaft, you know, and small d is the inner diameter of this hollow shaft with corresponding subscripts. Okay, so first of all, let us use the torsional equation, and we know the relation between the power transmitted and the torque is given as P is equal to 2 into pi into t into theta into n, 2 pi n, 2 into pi into t into n divided by 60. So here We don't know torque transmitted torque is different from alloy and mild steel shaft, different from steel and hollow shaft. So that is one is for hollow shaft, it is for TH, and for solid shaft, it is from TS. So power transmitted, if we make the ratio of power transmitted both type of steel and hollow shaft, so power transmitted by the hollow shaft divided by the power transmitted by the solid shaft is equal to torque transmitted by the hollow shaft divided by torque transmitted multiplied by RPM transmitted or angular speed transmitted by the hollow shaft divided by angular speed transmitted by the solid shaft. Pi and 62 into pi and 60 are same for both these equation in numerator and denominator. They are cancelling each other. So we have this relation here. And now from the torsional equation, we can replace the torque transmitted is equal to J into shear stress divided by radius, and this relation are applicable to the solid shaft also. We are putting the same value here, Js into tau s divided by Rs, and omega h omega s. So the relations are, this equation thus becomes like this: Jh by Js, tau h by tau s, ds tau s by tau s, ds by dh, which is diameter of the solid shaft and the hollow shaft respectively, omega h by omega s, angular speed of the hollow and solid shaft, and Jh, the polar momentum shear hollow and solid shaft, and tau h and tau s is that shear stress transmitted from hollow and hollow shaft. So we have certain relation. We know what is the relation between pH and PS, that is equal to 1.3, that is 1.32. So we put the 1.32 here, and we replace JH and JS by the formation by d to the power h to the power 4 minus dh to the power 4 divided by d to the power 3 to the power s divided by dh multiplied tau s, and tau s is given, is relation is given as 1.3. Diameter of the outer diameter of the solid shaft that of the hollow shaft is same. So this ratio is equal to 1, and speed of hollow shaft to that of the solid shaft is given as 1.1. Putting all this value, we have what we have, and at the same time we know the value of DH, means diameter of the solid and hollow shaft, that is 300 millimeter. So put this value even. So this relation will reduce to 300 to the power 4 minus small d h to the power 4 divided by 300 to the power 4 is equal to 1.32 divided by 1.3 into 1.1. Thus, solving this equation, we get the inside diameter of the hollow shaft, which is given as 1.158 millimeter. The last problem of this equation, let us discuss. Of this formulation is like this: reduce an expression for the allowable twisting moment of a thin wall tube. Also find an approximate expression for the strength weight ratio of the such a tube. So we have a tube, means it is a hollow shaft. So what is the, let us do, we want to explain the allowable twisting moment. What is the maximum twisting moment it can carry for a given value of the shear stress, and for approximate expression of the strength and to the weight ratio of such a tube. What is the ratio between strength and weight of this tube that we are supposed to calculate? So thinner tube in expression, we know, just I've told you. Next, what is the twisting moment? Let T is the thickness of the tube, capital D is the 2 into capital R, where capital R is the radius of the outer radius of the tube, and capital D is the outer diameter of the tube, and small d, as T be the thickness of the tube is assumed, the small d or inner diameter is given by 2 into R minus 2 minus T, 2 into R minus T. Thus, the polar momentum ratio of this type of tube is given as pi by 32 to the power 4 minus small d to the power 4. Put the value of D in terms of R, where D is replaced by 2R and small d is replaced by 16. Is replaced by 16, means 2 to the power 4 is equal to 16. R minus T to the power 4 is put here. Now, after further simplification, we'll have, because here also 2 is there, 2 to the power 4 is 16 here, so 16 is common here. It will can reduce this 32 into 2, so pi by 2, R to the power 4 minus R minus T to the power 4. Or after calculating after solving this equation, r to the power 4 is equal to r square minus r square plus t square minus 2 into rt to the power 2. Again, we are neglecting the higher powers of t because t is very small. For t, there is one specialty is thickness is very small. So inner diameter is more or less is very near to the outer diameter. Thus, this relation, we have the square of this t, square of the t is neglected, and square of the t square is also neglected because it's too small. This relation is reduced to r square minus 2 into r into t into whole square. The square of the t which we are eliminated or neglected. So this relation becomes r square minus 2 into r into t. This is the important thing we have to understand because otherwise the calculation will be too complicated. So put it here, r square minus r to the power 4 made the square. This will reduce to pi by 2, 2 r to the power 3 into t, 2 pi r to the power 3 divided by t. Thus, the relation between torque and ratio is we put the value of J here, it will become tau into divided by r. 2 pi r square t into tau r. That is the relation between torsional moment and the shear stress. Strength and weight ratio, we could go through the cross-section area of the shaft, which is after neglecting t square, we can 2 pi r t. And weight is specific weight of the tube. So the weight of the tube A into L into omega, it replaces what R is A is replaced by this value of R. This relation will become. So